Hi, I'm Scott and I'm studying a PhD of physics here at UNSW. The field that I study is solid-state physics. And the thing that I'm most interested in is creating a new type of electronic device. So sort of the history is that in about the 1950s, the physics of semiconductors was understood, and they were used to create all the components that are in your iPhone and in modern computers. Now today, what we can do is try to make a new type of semiconductor electronics. And that's sort of what I'm focusing on. Now the idea is that the new type of electronics would use quantum physics, which is very different to classical physics. And since they have a different operation mode, they'll be able to do different things to what regular computers could do. And we call this new type of computer that we're trying to build a quantum computer. Now in particular, the device that I'm trying to build is called an artificial atom. It's called an artificial atom because it's a transistor that's so small it can confine single electrons the way that atoms confine electrons. Now the reason it's like a transistor is that the device has a channel for electrons to tunnel through or travel through, and also has a gate on top of the channel to control how quickly or how many electrons can get through. The thing that's different about an artificial atom is that the gate is able to set it up so that only individual electrons can travel through the device. For each electron to travel through the device, it has to quantum tunnel through a barrier. The idea is that you've got a channel here and a level on the transistor for the electron to get to. But we put an energy barrier, sort of like a hill, in between. Now in classical physics, the electron can only get to that level if it has enough energy to go up and over the hill. But in quantum mechanics, there's always a possibility for that electron to not have enough energy to get over the hill, but still tunnel through it. And so this quantum tunneling is what we can use to study these devices and what makes them a quantum electronic device. So the equipment I use to study these devices is behind me. We use this thing here called a dilution refrigerator. The idea is that this refrigerator can actually get to minus 273 degrees Celsius. It can go to 14 millikelvin above absolute zero. So that's colder than outer space. And what we do in this fridge is we cool our artificial atom down to almost the coldest temperature ever achieved on Earth. And we apply magnetic fields of up to 5 or 9 Tesla. The idea is that the magnetic field can separate the spin states of the electrons in energy. So electrons have two possible spin states. They can spin up, which I like to do with my thumb, or they can spin down. Now by applying a large magnetic field, we can separate the energy levels of the up and down spin states, and then we can look at when the up electron is able to tunnel through the artificial atom and when the down electron is able to tunnel through the artificial atom. And the idea is that this will just give us some important information about how these devices operate. And then once we have that information, we can look at using them to do quantum computing, so implement them into a computer. And also, there's going to be a lot of different applications for this stuff that no one's even thought of because they're only just being discovered now. I chose to study a PhD in physics sort of after following through the trajectory of high school to university to PhD. In high school, I studied Extension 2 maths, physics, chemistry, and English. So when I got to uni, I did all the same things. I studied maths, physics and chemistry in first year, and physics was my worst mark. So that's what I chose to study. I found physics the most challenging. It was really heavily maths-based. It was making me think in ways that I hadn't really thought before. And the experiments that we were doing really were teaching me about stuff that happened in real life. That's sort of what I got addicted to. And I went through 4 years of undergraduate physics. And then at the end of my undergraduate, I sort of had the option to finish up university and go out and try and find a job, or I could stay at university and move into research, which is what I chose to do because I guess ever since high school I thought it would be really awesome to be the first person to ever learn something. And that's really what I'm getting to do here. I'm the first person to study a certain thing, and I'm getting to teach the world. It really feels like I own something about physics.